So my plan is to take the same example and build it inside ETABS. If we give that assumption to this ETAB, then only ETAB gives the manual calculation value, this value. It's okay, isn't it? So you can see the manual calculation and the ETAB calculation is same now. So this structure is not going to be balanced. Okay, so this joint movement should be balanced. Okay, as engineers, you know that the physical connection happen at the column face. You can see the beams in the column face, not in the column center. This joint is going to be balanced. So if you go for the extra. Hello everyone, welcome back to Structural Sri Lanka. In today's video, we are going to explore a very important practical topic, the comparison between manual frame analysis and ETAB frame analysis. We will walk through a real example. Let's take from the Google. Okay, so I'm already found an example, so you can search moment distribution method like that, so you can see this site. Okay, learn about the structures, so go to that site, and here you can see here the moment distribution method for frame. If you select that one, you can take this example. The reason why I chose this example, they clearly mention about the things correctly. Okay, so you can see here from the beginning, so they first of all they introduce the relative stiffness, how it should be decided. Okay, so they found the relative stiffness here, and from that they found the distribution factors. This is the way that how to find the distribution factors, and using the free end moment diagrams they found the moments. Okay, so using these things they have used this distribution table, so they finally found out the moment value after the distribution. So then they found the reaction values and the shear values, all the things. So in this example they have clearly mentioned everything about the moment distribution. So my plan is to take the same example and build it inside ETABS. So I'll show you how to correctly set up the frame and adjust the model to match manual condition, and explain why you might get different result. Because let's we design a ETAB model, then I will show you these values is not coming from the result, from the ETAB result. Okay, so I will show you. Okay, that one I can show you, so you can go to the ETAB. So I minimize this. So I will very quickly going to design that model. So I can tell you what is the missing in the ETAB models. So how to simplify or modify the ETABS model to reflect the textbook conditions. Okay, and moment distribution actually behave in the both methods. So I can show you those things. So it's okay. So we can start a new model. So don't think about the code. So whatever the code it is, okay. I will click OK, and I can modify my grid after this. So one window is enough for me, so need other things. And if I am right click and go to the add modify, so I can modify my grid Jiva. So what is the values? So you can see in the frame, so A to B 5 meter, and the B to C 4 meter and 3 meter, and 4 meter height and 2 meter height, and 8 kilonewton point load is in the overhang member, and 2 kilonewton per meter UDL values is A to C. So the moment of inertia of this member is 2I, and this vertical section moment of inertia is I. So we can model this thing like in ETABS. So I'm going to display grid data as spacing, so it is very easy to model that. So 5, then 4, then 3. So here I don't need any x values here, y value I don't need, so I can click OK. So I will just put 1, then I only need 2 stories, so I can delete other stories, and the story height should be 4 and 2 as example. So it is okay. So I'm going to elevation, so I can click 1 and okay. So here some important condition is there. So we are going to analyze this frame in the XZ frame. So we need to change the degree of freedom for the XZ frame. So for that you want to go to the analyze, set active degree of freedom. So you can choose the XZ plane. You can see X and Z. So XZ plane. So then click OK. In the example, they told that the same E values should be we need to take. Okay. The E value should be same. Then in the example you can see the when they find the distribution factor, from this you can identify that the E value should be same in the every member. So from that it's take 0.286. So if I'm going to define concrete material, so you know that the concrete E value is this one. So E value is not going to be changed because I'm going to use the concrete section, and the I value. So I can go to the define section properties and the frame section, and I will choose the concrete beam, and I will the concrete beam section and the column section I'm going to choose same. Okay, so I can modify this one. So I will choose 300 by 300. It is okay. So this is a column B. So I'm going to modify show modifiers. So I'm going to multiply the stiffness matrix by 2. Okay. So moment of inertia I'm going to double, because in the example you can remember the horizontal member moment of inertia is 2. So I will multiply this. Okay, then I can click OK. So here if I go to the show section properties, you can see this value we can't change. Okay, so that's why I choose set modifier values to increase by 2, this multiply by 2, and you can click OK. So I choose concrete column for the vertical sections. So go to the modify, and you can change this as 300 by 300, and it is click OK. And if you go for the set modifiers, keep it like that. So because the column value if we take as I, so beam value is 2I, so it is okay. Then delete these things because we don't need these things. Then click OK. So we can draw the beam. Then first of all I'm going to draw a beam here and here and here and here. Then I will choose the column. You can select like this, and you can click like this. Okay, so it is okay. So what should be the value? 2 kilonewton and 8 kilonewton point load is there. So no other loads I can found in this example. So here, okay, so here I want to go apply the restraint first. Okay, so assign joint restraint. So this is the pin support, and these 2 points are the fixed support. Okay, as per example it's like that. And these two, there is a uniform distribution load. So go to the assign frame load and distributor, and you can select a dead load. So you can give 2. So in my previous video I told that for the model, don't use this dead load to apply the loads here. Okay, because the weight of the component going to be increased by like that. But in the example you can see the self weight is not going to be considered in this example. So we need to delete the self weight. So we can do like that. Before I apply this load, I will go to the define and the load pattern. So if I change this self weight multiplier 1 as a 0, then what happened? The self weight of the component not going to be considered furthermore. Okay, so if I change this 1 as a 0, this work as a super dead load pattern. So from hereafter, the component self weight not going to be considered for the analysis. We know in the moment distribution, in this example, they didn't consider about the self weight. Okay, they didn't consider about the self weight. You can see 2 kilonewton as per the example with this value. We can find that they didn't. You can see 2, the length is 5, it's square by 12. So they didn't consider about the self weight. So I'm going to remove the self weight. Okay, so for that we can do 2 ways. Okay, the first one is we can change this 1 as a 0. So then hereafter this dead load work as a super dead load. Okay, because by applying the loads by this dead load, not going to increase the self weight, because the multiplier factor is not 1, it is 0. So you can give the load for the frame. Okay, so if you keep the dead load self weight multiplier as a 1, what you can do, you can go to the section properties and you can just choose the weight factor as a 0 like this. So I'm going to do in the example, I'm going to change this 1 as a 0. Okay, then what happened? The component self weight not going to be considered. So I will do like that. So if you like to keep this as a 1, so you can do, so go to the define and the section property, and if you go to the concrete beam, then go to the show modifiers, the weight factor 1 you can change it as 0. Then what happens? The beam self weight not going to be considered. So you want to make 0 in the beam and the column. So if you think if you have 10 components like that, so every component self weight multiplier we need to make it as 0. So it is difficult. So it is easy way is go to the load pattern. So if you change this as a 0, the component self weight not going to be considered for the analysis. So it is very easy. Okay, so I'm going to make it 0. So now we don't have any problem to assign the loads. So go to the like that. So you can give the 2 kilonewton per meter. So here we have the point load. So go to assign frame load and the point load. In the corner of the member we have 8 kilonewton. You can see here. As per the example, we have assigned the loads. Then if you run the model, we can check the bending moment value. So I will save as the model test 1. So let's take time to analyze the model. Okay, now what you can see here, if you go to the moment diagram, you can see. So I'm going to shrink the object so I can easily find out the values. So here with the manual calculation, you can see, if you go to the moment value, this is BA is 3.55, 1.3 and 2.24. Okay, so BA mean this is the BA, it should be 3.55, not 3.5, it is 2.5 something. So you can see the values is not going to be same, okay, with the manual calculation. So if you take the BE component, this BE vertical member, so if you go to the BE, if you take in the BE joint, the moment value should be 1.13, it is 1.01. Okay, so what happened? So moment values is not correct. What can be the reason? The reason is, in the manual moment distribution, we only consider about the EI values, okay, and ignore other real world effects. But in the ETABS, the model includes many hidden things: axial force effect, shear deformation, torsion, and more. That's why the result may not match the directly unless we carefully simplify the ETABS model to match the manual assumption. So with this example, I will show you how to do that. So we need to match this value for the manual calculation. So there is a problem. Why we only use the EI values to analyze these models, okay? So in this analysis, we didn't consider about the shear deformations, torsions, axial forces. We didn't consider. Only the thing that we consider is EI value. Okay. So what is the reason behind that? The reason is, in this moment distribution method is very classical, okay? Simplified method developed by Hardy-Crews. You know that? The Hardy-Crews found this moment distribution system. It is early 20th century, long before, okay? Long before the computers. It was designed to hand calculate moments in the indeterminate frames using the paper and the calculators, okay? To keep it practical and the fast manual users, the method makes a few assumptions in the moment distributions. So we need to keep some assumptions, okay? So if you going to do the moment distribution, we assume the structure behave elastically. So we only need to worry about the bending stiffness. Bending stiffness mean EI, not non-linear effects or cracking. And the second one is, the moment distribution method only consider rotation at the ends of the member due to the bending. then it ignores axial deformation and the shear deformation. So these are the assumptions, okay, when we do the manual calculation. So these things we need to adjust in the ETAB to get these values. Otherwise, the ETAB didn't give this value. So actually, ETAB give the correct values, but we need to check the manual calculations. Okay, the manual calculation value should be same as the ETAB value. So in this example, I will show you how to match the ETAB model to take this manual value. Okay, so here I told you the axial deformation, that shear deformation, torsion, deflection, they didn't consider about these things in the moment distribution method. The goal is to solve only the joint movements, not the full deformation in the moment distribution method. Okay, usually the loads are applied as a point of uniform loads, and the self weight is either ignored or we can manually add, and there is no automatic calculation for the self weight like in the ETAB. Okay, so all members are assumed to have constant EI value. That means no variation along the length and no changes in the sections. So support should be either pinned or fixed or somewhere in between with simplified relative stiffness. Okay, so that means no springs, offset, partially fixed unless model by adjusting the K value. So these are the assumptions that we make to do this moment distribution. But that assumption is not going to do by the ETAB. So we need to give this assumption to the ETAB. So how to do that? If we give that assumption to this ETAB, then only ETAB gives the manual calculation value, this value. So for do that, I will model this as a new model. Then you can understand this very easily. Okay, so I'm going to model from the beginning, so it is okay. So here I need only 2. So here 2 and 4. Just x spacing 5, and it is x direction 4 not 5. It is only 1 is enough for me, and it is 1. Okay, so if you go to the elevation, then I will click this one, and I'm going to close one window, and I need to modify something. Okay, here you can go for the spacing, for it is easy for me, 5, 4 and 3. So this you can delete it. This one is 3. Okay, then modify, and 4 to it is okay. Okay, so I'm going to define a frame like this. Okay, so go to the add new property and take general section. So here I told you they didn't consider about the axial deformation, shear deformation, torsion, deflection, everything they didn't consider. So you can change these things as a 1. Okay, so here we can modify the section, so change all these value as 1. So it is okay. Then they didn't consider about these things. Okay, so we can manually add the E values. So just keep like that. So if it depend, and I will take a copy of this thing, and here go to the modify, and it's okay. So you can see here, and I'm going to multiply the I value by 2. Okay, I value going to be 2 in the FEC 2. So horizontal section I want to take F section 2. Okay, so it is okay. Then you can draw it. So F section 2 I'm going to use for the draw the beams here, 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 here. Okay, then I'm going to use for the vertical section FE section 1. If you can draw this that quick draw tool like this, so you want to give the restraint here, so go to the assign, join restraint, go the fix values, fix. So this pin, so for these two members we need to give the distributed load, and we need to give the value as 2, and for this section we need to give a point load. Okay, frame load, point load, so we can give 8 in the gravity direction like this. So now loading is okay, so assign the properties is okay. So by assign the frame section like this, okay, so this is very, you can see I change all the values as 1. Okay, so actually these mean actually there is it's like a no frame. So you can see the area is very small value, the moment of inertia values, the torsion constant, the everything I took very small values. So if I change this like this, the axial deformation, shear deformation, torsion, deflection, these values are going to be very low. So we can neglect these values. So that is why I chose the frames like this. Okay, so we using this, we define the section properties like this, we can match those assumptions that we are doing in the manual calculations. Okay, so if you run the model, before that you need to change this dead load self weight multiplier as a 0, because we are not going to consider the self weight of the component. So if you change this as a 0, dead self component self weight is not going to consider. So then okay, so you can run the model. So correct model, can save it like that. And after that, if you go for the moment to check the moment value, here some correction should be need. So if you go for this section, it is a 30 point something, so other values is something okay, so we need to check that. So if you go for this section, what happened, the section properties is steel column. Okay, so it is not a steel column. So if you go for the this one, and I'm going to check my frame sections. Okay, so you can see the frame section like this. Okay, so you can see this is the steel column, that's the problem. So we need to check this as a F section 1 like that. So go to the assign frame section property. So this F section 1. We can change the section like this. Okay, so run the model. And if you go to the moment, now you can see with the manual calculation. So here you can see the sections. This one A, B, C, D. This is F. This is C. So you need to keep remember that's joints A, B, C, D. This one F. This one E. So if you go for the values, so you can see the 3.55. It is the BA. So it is okay. 3.53. It is nearly 3.54. So values is okay, isn't it? So 1.30. So here you can see by right clicking this one. If you come to this edge, it is 1. If you take this value as we can say it is 1.3. Okay, nearly it is 1.3, 1.28 mean. So as a manual calculation, you can see the value is nearly 1.3. So 2.24 is 2.25. So that's the thing. So this value little bit difference. Okay, have a little bit difference because I mentioned that there are a lot of hidden things that the ETABS is consider, because they are using the finite element method to calculate these things. So the values may have small variations in the ETABS and the manual calculation, but it's not a different big difference. Okay, they don't have the big difference. If they have the big difference, there is a problem that you can see 3.55 here, that 3.54 nearly. So it is okay. So it is 0.01 difference. So if you take this is a 2.25, this is 2.24, means 0.01 difference is there. It's a very small difference is there. So actually it is okay with the manual calculation. So you can see this assumption is worked. Our assumption is worked when we define the section properties that I have mentioned before. So you can see this value is 1.13. Yes, okay, it is 1.13, and 12.17. So also okay. So 11.78. So 11.76. It's okay. This is 24, and it is 4.88. It's 5.88. So it's okay, isn't it? So you can see the manual calculation and the ETABS calculation is same now. So if you go for the reaction values, so you can check the reaction values here by the arrows. You can see if these values you can check by the manual calculation. It is 6.98 and 0.88. You can see 6.99 and 0.84. So 8.82, 14.72. So the values are okay, isn't it? So 9.68 and the 4.29, 9.66. The values are okay. So and if you check the share also, the values are okay. So now you can see the ETABS values and the manual calculations are same. So but first of all we need to give the assumption to the ETABS, otherwise ETABS never match with the manual calculation result. After this, if you go for the moment diagram, there is a special thing that we need to check. So this joint moment should be balanced. Okay, so you can see here this 11.78 and the 12.21, the total is nearly 24. that 24 match with this 24, so it is cancelled out. So this joint is going to be balanced from this moment, and here also like that. So 3.55, and the here value is 1.12, 1.3 something. So if we deduct these two and with this, so the joint going to be balanced. Okay, so this is 1 point, you can see the 1.28 something, which is nearly 1.3. If you go to, you can see it is 1.3 something. So this is if you from the 3.55, if we deduct 1.3, it is nearly for the 2.25. so that means this joint going to be balanced by this moment. Okay, otherwise it is a problem if the joint is not balanced. So I can show you an example. It is very simple example, but if you do it wrong, your whole model going to be wrong. So I can show you very quickly. Actually it is a bonus tip for me. And if you go for the take whatever the thing, no worries, go and close one window and take elevation here. This is very important. Okay, so it is very important. You see these things, most of the engineers also doing these things, but they actually didn't think about so much about these things. Okay, so I will take not a steel column, I will take a concrete column. Okay, so I will draw a concrete column. So here I am going to choose the default concrete column. So section size is not I draw like that. No problem. Yeah, concrete column. So if you draw like that, then I will draw a concrete beam here to here, and I'm going to assign a load. Okay, so I'm going to show you very interesting thing. I will give 2. Here I'm going to show you one interested thing. Okay, very important thing here. Sorry for the words. Then if you run the model, okay, model 1 like this. These things you never consider. Okay, so if you check the moment value in this section, with the value you can see you can see this joint moment is not going to balance, because you see the top moment is 14.89, this edge moment is 11.43. so this structure is not going to be balanced. Okay, so this joint moment should be balanced. Okay, as engineers you know that in these edges moment going to should be balanced, but you can see this is not like that. What is the reason? You can see it if you go for the extrude the frame. So you can go to this one and you can extrude frame. Okay, so from that you can see that you can go to the shells also. We need to extrude, I think. Yeah, if you go for the go for the 3D, you can see here. Now you can see when a beam connects to the column in reality, the beam doesn't stop exactly at the column center. The physical connection happens at the column face. You can see the beams in the column face, not in the column center. But in the ETAP default, it connects to the center line of the column. So what that means, the small distance between the column face and the column center line, that is called the end offset. So what you need to do, select this frame and go to the assign frame end length offset. So if you choose like this, now you can see if you run the model now, run the model. Now you can see this didn't happen well. You need to select all the sections. So going to the assign frame and end length offset. So you need to define length like that. The end I should be 0 and j should be 0. Then if you click and go OK, then you run the model. Then after that you can see our joint going to be same. Okay, if you don't model this correctly, the moment arm changes, okay, and the internal force, especially the moment and shears, become slightly incorrect. So now you can see, if you go for the moment diagram, now you can see the top column and the moment beam edges moment values are same. So that means these joints going to be balanced. So if you go for the extrude shell, you can remember the previous image. Then now you can see the beam is not in the column face, it's come to the column center. So like this the frame should be. So otherwise this joints moments not going to be done. So I think this is the new thing for you, and most of the ETAP designers don't know about these things, and there are only few people knows these correct things. And if you learn something new, if you want to learn something new like this, so please subscribe my channel, and thank you very much. So we will meet the next section. So next section is going to be very useful. So I'm going to do a manual calculation and the ETAP calculation and the pro-con analysis. The columns and the beams, I'm going to show you how to do that correctly and how to take the bending envelope correctly manually in the pro-con and the ETAP. So we can talk everything in that session. So Thank you very much. Okay.